And torque is defined in two ways. Torque is defined in two ways. It's the cross product of R and F, right? Where R is the radius. It would be the distance. So take this as the pivot. It appears like something rolling down, but I meant it to be a pivot. And you're applying a force here. So the force is applied at that point, and it's a rolling. You're applying the force at that point. What is the torque? Let's say that the angle here is given as theta. So how do you calculate the torque in this case? You can answer to these questions. Torque is basically RF sine theta. So if I give you the radius as 3 meters and the angle is, let's say, 60 degrees, then you have to be careful about which angle. The angle is the angle between the line of action of the force. Isn't that the line of action of the force? And you can talk. Come on. Line of action of the force and the radius. Isn't this the radius?
Yes.
So in this case, it's the actual angle that I've given. But you got to be careful. I might give you the other angle, you know what I mean? And then you should know, hey, it's the angle between the radius and the line of action of the force. Take that angle. So that's what you have to be careful there. That's a simple thing to remember, isn't it? So if I give you the force as 10 newtons, and then you should be able to calculate the torque. In this case, it's 3 times 10 times sine of 60. Can somebody tell me what you get for that? 25.9. And what's the unit of torque? Meter Newton. RF. R is in meters, F is in newtons. So meter Newton. That's one thing, one way. The second method of calculating torque is remembering that torque is a vector and it's the cross product of R and F. So this one I have tested you many times. So R will be given as an ijk vector, so the same with F, and you know how to take the cross product. So that is one topic. So the second topic is rotational motion. So rotational motion has similar equations like in linear motion. Remember, in linear motion? But before we get there, we define quantities like alpha, angular acceleration. Remember, angular acceleration is what? D omega by dt, change in angular velocity by time, and omega is d theta by dt. And you have all those in your formula sheet. You just have to know. And then there are kinematic equations that come up like omega final is equal to omega initial plus alpha t. Isn't this similar to Vf is equal to V naught plus AT? So make those connections. And then you have those. This is another one. Then you have we called it the king. So what's that? That's going to be delta theta is equal to omega naught t plus 1/2 alpha t squared. And do you remember force is mass times acceleration? What is the corresponding formula in rotation? What takes the place of force? Remember, you came very close. Force moves an object in a straight line. Torque rotates it. So force is mass times acceleration. Torque is I alpha. I is what? Rotational inertia. For a disk, it would be mr squared by 2. So there are one or two I's that you should know, and it's not on your formula sheet. One is I is mr squared by 2. Rotational inertia of a disk. M is the mass, r is the radius. Then for a particle, that's what you start with. For a particle, it's mr squared. Basically, these two. So torque is I alpha. I heard somebody say, I thought it was I omega. I times omega is angular momentum. Right? Remember, angular momentum is I times omega. It's okay. So I don't want to go there. So I think if you know these, you will get the second one. And you know what each one stands for. Should be able to figure that out. Theta should be in radians, not in degrees. You know how to change from degrees into radians? You know, right? Pi by 180, multiply by pi, divide by 180, where pi is 3.142. Okay. 90 degrees is pi by 2. Do you all know that? Okay. That's what I'm talking about. Also remember, omega is 2 pi times F. F is the frequency. When it comes to springs, force in a spring is negative K delta X. K is called the spring constant. Delta X is how much it stretches or it's compressed. This is a lab that we did, so you should know. And usually F is, like if there is a mass here as shown, what is F? Huh?
mg.
mg. So just remember that in this case, F is mg. So you put mg is equal to negative K delta X and find K. And then the time period of oscillation of a loaded spring, and this is for a light spring. In the lab, we used the heavy spring, so we took 1/3 of the mass of the spring, added it, right? But on the exam, I'm going to talk about a light spring, and it'll be M by K, where M is the mass attached in kilograms, and K is the spring constant. You got it? And how is time period related to frequency? How is... Because maybe I ask you about what's the frequency of oscillation? One over time. So just remember that. Frequency is 1 over time, and you will be good. So Bernoulli's principle, a liquid flowing through a tube like this with different cross-sectional areas, where we say this, the area here is caps A, and the area here is little a, and the velocity of flow is going to be caps here. So first of all, you have the equation of continuity, which says that the rate of flow multiplied by the area should be, oh, I made a mistake there. The rate should be the same, like that. In each part, area times velocity should be equal. That's called the equation of continuity, and this gives the volume flowing per second. Volume flowing per second. That's what it gives. So if I ask you to find the volume flowing per second, that's what you would do. Take either of the areas, multiply with the velocity in that area, okay, in that cross. And then you have Bernoulli's principle. Always applied to a horizontal pipe. What is the basic idea of Bernoulli's principle? There are 3 types of energy. So let me bring it out from the beginning. Pressure energy plus potential energy plus kinetic energy is a constant. You recognize potential energy, gravitational potential is mgh, kinetic energy is half mv squared, everybody knows that. And once we did thermodynamics, you know that work done is P dV. Remember, anybody? That's where we get pressure energy from. Pressure times volume. But you will never find it in your formula sheet this way. In your formula sheet, what is done is, this is divided throughout by volume. Either by volume or mass. It could be either volume or mass. We'll do it both and we'll see. So it's P, is it by, okay. If it's by volume, you're going to get, watch this, no confusion. Is that easy to understand? First term, volume got cancelled. Second term, mass by volume is density, isn't it? Second and third term. So you could write it that way. But if you were dividing by mass, which I think is how it's given for you, after having written that, then I realized. So I'm writing this original one again. And then if you divide by mass, it looks a little different. How does it look now? What's the first term? Pressure by density. You see volume by mass? So it's 1 by density plus GH plus half. Is this how it's on your formula sheet? Right? And if it's a horizontal pipe, then you don't even have to worry about one quantity. Which one? GH. GH will be the same on both sides, so don't even worry about that. That makes the formula even easier. Now, all you got to remember is P1 by rho plus 1/2 V1 squared is equal to, I just realized I was using little v and small v. Anyway, P2 by rho plus 1/2 V2 squared. Don't make any sense. Unfortunately, I used V1 and V2, and I was supposed to use caps V and small. I can change that. Because in the diagram it's capital. Know what I'm saying, right? So what is P1 and P2? P1 is the pressure in this part, and P2 is the pressure in small part. Where do you think, two questions, where do you think it's flowing faster? Smaller one. So where is the pressure lower? Smaller one. That's Bernoulli's theorem. Where the velocity is higher, the pressure is lower. So the next topic is conservation of momentum in 2 dimensions. So let's say that you have mass 1, mass 2. So that's mass 2. This is mass 1. Before collision, the velocity of this is v1. This one has velocity v2. And after, their velocities become v2 prime and v1 prime. So those are the things. Also, you need the angle. So let's call this as theta 2, and this angle is theta 1. So how do you apply the conservation of momentum here? What's the first thing you would do? 2D, you have to break it up into x and y. The initial momentum is only along which axis? X-axis. So the y is 0. You remember that? So if you take the component of this along the x-axis, what are you going to get? What are you going to get? M2 V2 prime cosine theta 2. Do you know how I got that? Because when you set that triangle, when you set up that triangle, this is going to be the adjacent side. This is the triangle I'm talking about. You see this triangle? Am I right? Or not? I'm talking about this side. This side would be the adjacent side, isn't it? This would be the opposite side of the angle. So the adjacent side is cosine. Same thing here for the other one. It would be what? M1 V1 prime cosine theta 1. Okay. So when you apply the principle of conservation along the x-axis, what are you going to say? Along the x-axis. M1 V1 plus M2 V2. Isn't that the initial momentum? Should be equal to the other two. Oh, right, that's a lot of writing. Yeah. Cosine theta 1 plus M2 V2 prime cosine theta 2. That's along the x-axis. What about the y-axis? Y. What's the initial momentum along the y? 0. So a big 0 is equal to What are the vertical components? The vertical components are going to be here, coming up. What are these components? This would be M2 V2 sine theta 2, and the other one would be, well, don't put a minus there. If you're putting a minus, you could be in trouble. The minus comes, you can do it either way. Okay, let's go with the minus. So this would be M1 M2 V2 sine theta 2 plus M1 V1. What did I do? Something. Okay, V2 prime. This is V2 prime. V1 prime sine theta 1. The thing is that if you leave it as positive, when you take it to the other side, you get a negative. You can see that mathematically. So be careful on that. Don't already put a negative there. So that's the conservation of momentum. And then depending on what I'm going to ask you, because it's 10 questions, I might ask you to find the angle or something. I might even tell you that after collision, they stick together. You remember that question we did? After collision, they stick together and they both move off at a certain angle. Now, that actually becomes an easier question. Because now all you got to do is you add their masses and then take the components. See? If they stick together, are you getting what I'm saying? If they stick together, then the total mass is M1 plus M2, and then you take the components, you'll have only one each, and be careful about that. So if you have a rod of a certain length, L0, and you heat it from temperature T1 to T2, then what is the change in length? What is the formula for thermal expansion? Change in length is equal to the original length times alpha, which is the constant linear expansivity. Remember, this is the last lab we did, times change in temperature. That's it. Go ahead. But see, whenever you have a doubt, always change into Kelvin. Because Kelvin will always work. But in this case, Celsius would work because it's the difference in temperature, change in temperature. But if you ever have a doubt, just change into Kelvin. Remember. So the next topic is Carnot's engine. In Carnot's engine, you have a source and a sink. The source is at temperature TH. The sink is at temperature T. What do we use? C? Yeah. Okay. TC. This is the working substance, in that 3D thing. What is the working substance in a Carnot's engine? Air. In Carnot's engine, it's an ideal gas. In real engines, it's air. Okay. So this is an ideal heat engine. Yeah. So how do we define? There are other terms. QH is the heat absorbed by the ideal gas, and QC is the heat rejected. QH is the heat that it takes, and QC is the heat that it gives to the low temperature one. And work, yes, there would be work. And what is the work? Work is QH minus QC. And efficiency is defined as work over QH. That's the first formula. But if it's going to be a percentage, then you have to multiply by 100. You know that. So, and then the second formula is when you substitute for work. Isn't work QH minus QC? So automatically you get QH minus QC divided by QH. Just substituting for work. And then the third formula is, who knows, in terms of temperatures, similar. TH minus TC over TH. Here, temperature's got to be in Kelvin. Because remember, Kelvin got the idea for temperature, for the absolute scale from this. Has to be in Kelvin. I'm telling you, because some people look at this and say, but isn't it the temperature difference here? Yeah, on top, but what about here? That's a standalone, isn't it? So on top it's the temperature difference, but down it's, so please change into Kelvin. All right, so the next one is static equilibrium, and this shows the, what is that? What force is that? The weight, yes, that's the weight of that bar acting through the center of gravity. So let's say it's that. And you know weight is mg? Okay. And there are two masses here. We'll call them m1 and m2. Now, what are the other forces that act? Wouldn't there be two reactions? Supports? Two reactions. Let's call them whatever. N1, N2. Because they are normal reactions, right? Perpendicular. Those are the forces. And then there are two supports. So A and B are the supports. What are the two conditions for static equilibrium? Two conditions. What are they? Net force is equal to 0 and net torque is equal to 0. Let's apply both. First, net force equal to 0. There are forces acting up and there are some forces acting down. So aren't we saying that the total forces acting up is equal to total forces acting down? So that means N1 plus N2 is equal to, you got to be careful there.
Would it be N1 plus N2 plus N2?
Yeah.
Would that work? Yeah.
Would it be the same?
So it would be the same. Work plus M1G plus M2G. Because M1 and M2 are masses, they are not forces. So you have to multiply it with G. Got it? Right. Next is the part where you consider the torque. So you have to pick a point. You have to decide where you're going to calculate the torque about. And usually we take the point at the left. You could take it anywhere. So focus on this point here. That's where we're going to calculate the torque. If you focus on that point, tell me what is the torque due to N1? 0. And N2 is going to be, is it counterclockwise or clockwise? N2. It's here, N2 is acting up, it's counterclockwise. So N2 is trying to rotate it counterclockwise, but all other three are rotating it clockwise. So how do you calculate the torque? Torque is what? Force multiplied by the perpendicular distance, isn't it? So M1G, what's the distance? I need to label. C, D, E. Okay. M1G times
C.
A and B. Shift A and B there. So AC, right? M1G times AC plus the weight times AD plus, come on, M2G times AE. Remember, we're taking all the distances from A because we picked that point. Those are the clockwise, should be equal to the only counterclockwise, which is N2 times AB. You do the math, you get the answer. So this is motion of an object down an inclined plane with friction. So what are the forces acting? So you will be given this angle, theta. The forces are, you got to help me. What are the, no, first, let's go with the original forces. Mg, the weight. All right, and then the normal force. Do we call it N or Fn? Whatever, we'll call it N. And then, friction always opposes motion, isn't it? So you have to read the question carefully. If the object is being pushed up, then you have two forces coming in. Number one, the force you're applying, and then the friction. But if the object is coming down, you only have friction opposite, right? Okay, so in this case, let's say it's coming down. If it's coming down, then I have to show friction that way, shouldn't I? It's coming down. Object is sliding down. Then you have to brake mg into its components. What are the components? Mg cosine and mg sine. He walks in and says, mg cosine theta and mg sine theta. And then you look at the x, we rotated the x and the y axis. Remember, the x axis is now like that, and the y is like this. So, what are the forces along the x axis? Forces along the x. Friction and mg sine theta. Obviously, it's coming down, so mg sine theta should be. You can either go with the coordinate axis system, where to the left would be negative, to the right would be positive, or you could go practically. Which one do you want me to? Practically, what direction is the sliding in? Down. So which one should be greater? Mg sine theta. So we'll go with, I use caps, mg sine theta minus friction. Isn't that the net force? And according to Newton's law, net force should be equal to? Oh, nobody knows Newton's law. Net force is equal to mass times acceleration. Net force is mass times acceleration. What about the y-axis? What is the net force along the y?
M plus mg cosine theta.
Along the y. So remember that the normal force is upwards and mg cosine theta is down, and this object is not moving along the y-axis, is it? No. Therefore, n must be equal to mg cosine theta. That gives us a method of calculating friction, because we know friction is mu k times n. Do you know that? So once we get n, you go, okay, it's mu k times mg cosine theta. So we got our friction. Once you get your friction, you simply take that, plug it in here. Okay, let me write the whole thing. So now mg sine theta minus mu k mg cosine theta is equal to m times ax. Why do we need mass in all those? Let's cancel them out because they are in every term. Okay, gone. So there you end up with a ready-made formula for acceleration. Ax is g sine theta minus mu k cosine theta, which is one of our labs. All right, so mu k g cosine theta, I missed the g, now it's been added. So it's an object supported by two strings. An object supported by two strings. Let's give the mass of this as m, and the angles are given. This is theta 1, this is theta 2. Remember, the angles may be equal, could be, but generally they are not. So theta 1, theta 2, and you're asked to find the tension in the strings. Yeah. The tension in the strings. Let's call it T1, T2. Okay. So you know that this point, whatever we call it, maybe P, that point is not moving. Is it moving? No. So it's in equilibrium. That means the forces acting on it should be balanced. The forces, but the problem is the tensions are neither along the x-axis or the y-axis, are they? So you break it up into its components. First thing is what you do is you break it into its components. Okay, let's go. Try. What is this going to be? What's that component going to be? And so that would be T2 cosine theta 2. We are breaking T2 into its components first, yeah. And so this would be T2 sine theta 2. Do the same with T1. You know what I'm saying, right? Okay, so what do you get for this? This is T1, what? T1 cosine theta 1. Similarly, you have I'm going to drop it a little short so you can possibly make the difference out. And that would be what? T1 sine theta 1. And then apply the idea that the net force must be 0, both along x and y, isn't it? Okay, so take the case of the x-axis first. What do you see? The x-axis, what do you see? This force and this. Shouldn't they cancel out? Okay, so you're going to say T1 cosine theta 1 is equal to T2 cosine theta 2. That's on the x-axis. And then on the y-axis, what will you say?
T1 sine theta 1 plus T2 sine theta 2
Right.
not is equal to mg.
Very good. T1 sine theta 1 plus T2 sine theta 2 is equal to mg.